All right, now for a video on the law of cosines. So the law of cosines is kind of partner to the law of sines. They have similar names. And the law of cosines is so named because it has cosine in the formula. So the idea is, again, we have a generic triangle. This could work for right triangles, but can work for, any triangle. And we label our angles A, B, and C. And if that's how we label them, then our sides are going to be opposite of A is A, little a, and opposite of B is little b, and opposite of C is little c. And so when we're referring to our generic triangle, this is the triangle we're talking about. So the formula for this is going to be little c squared equals little a squared, plus little b squared. And if you recognize this, so far it's the Pythag formula, Pythagorean theorem. So what this really is a formula that takes the Pythagorean theorem and modifies it. We're going to put a little modifier over here that makes it work for any kind of triangle. And it turns out that whenever we use Pythag, we're actually using the law of cosines. But this angle I'm going to plug in here, cosine of an angle, when that angle is 90, right, when we're dealing with a right triangle, all of this stuff over here disappears. So it's going to be all a separate term, and that term is going to disappear when the cosine of 90 is there. And when it's any other angle, it's going to be there, and that's going to modify our Pythag formula to make it work for any triangle. So this modification is minus 2 times side A times side B times the cosine of the angle opposite the side we are solving for. So see, this is solved for c squared, so it's going to get us this side. This right here is going to be big C, the angle C. And again, I'm doing that in orange so you can tell the difference between the C's. The little c here refers to the sides, right, like Pythag. And here's the angle C, the angle that is opposite side C. So this is the formula. We have Pythagorean theorem with a little modifier here, this term right here. And again, when cosine of C is 90, so cosine of 90, that's going to be 0. And 0 times all this stuff makes it go away, and what we're left with is just Pythagorean theorem. So that's where it goes when we're doing this for a right triangle. So let's practice utilizing this formula on a generic triangle. Again, this works for right triangles, but the beauty is that it works for all triangles. All right, so I'm going to say that this angle down here is 45 degrees, and I'll also say over here is 30 degrees. So there's that. And I'm going to be solving for side C, so let's put side C right here. And I'll put side A and B, I'll label those with actual numbers. So maybe let's do 5 and have this be 6. How about that? So you'll notice right away that the formula only requires one angle. It requires angle C. So we don't really need this 45 here. It goes with this 5. We're not solving for 5. We already know what 5 is. We're solving for C. So C will be our side we're missing. A is going to be either the 5 or the 6. Let's have it be the 5. B will be the 6. Again, minus 2 is a constant. We have 5 and 6 here. And then we'll have cosine of the angle that's across from C. So again, don't be misled by just these random angles that are thrown here. We don't need the 45-degree angle. We need the 30-degree angle because that's the angle that goes with side C. So let's fill out our formula. Instead of c squared, I'm going to keep c squared because I'm going to solve for C. And then I'm going to have a squared plus b squared. Well, again, a and b, it doesn't matter which one you call which. So I'm going to call a 5. So it's going to be 5 squared plus 6 squared. Again, the 5 and the 6 came from above in the triangle. And that's going to be minus 2 times a times b times the cosine of angle C. Well, it turns out that since we said a and b here, 5 and 6, a and b are 5 and 6 here. And the cosine of angle C is going to be 30 because that's the angle across from C. Again, always look for that association. The side we're looking for is always going to have the angle here that goes with it. So that's going to be 30. Let's write that in blue. So 30 degrees. So there we go. So now we just do some basic math. We do 5 squared, which is 25, and then 6 squared, which is 36. All of this is all multiplication. It's going to come out negative. It's going to be negative 10 times negative 6, which is negative 60 times the cosine of 30. And that's going to equal, again, c squared, the c that we're looking for. So it's really tempting to put these together and subtract 60 from them. But notice the minus 60 is going with cosine, whereas these guys are just regular numbers. So we can put these together, but we're not allowed to subtract 60 until we multiply it by cosine of 30. So when I put these together, I'm going to get 61. Now you'll notice that 60 and 61 are really close, so it's incredibly tempting to subtract those. But again, we cannot because the negative 60 is with cosine of 30. Let me scoot this up a little bit. So now we're here. So the next thing we want to do is we want to simplify the cosine of 30. We do know the cosine of 30 if you look earlier on our, oh, where'd they go? Our special right triangle diagrams. I guess I got rid of them. Let me copy down the original problem, or where we left off at least. C squared equals 61 minus 60 cosine of 30 degrees. All right, so if we look at our special right triangle, we need a 60, 30, 90 because we want to know the cosine of 30. So there's my right angle. Here's 30. Here's 60. And remember, when the hypotenuse is 1, a 60, 30, 90 triangle has the opposite of 30 being a half. That's what you need to remember. And then you can use Pythag to solve for this side, which is root 3 over 2. Again, you can also memorize that. So we have cosine of 30 is what we're looking for. And remember, cosine, unlike sine, which is SOHCAHTOA, opposite of our hypotenuse, cosine is the ca, right? So ca and then toa. And ca stands for adjacent over hypotenuse. So here's 30. The adjacent side is the side that isn't the hypotenuse that's next to 30. So it's right here. Kind of hooks down, right? That's the adjacent side. So it's going to be the adjacent, which is root 3 over 2, over the hypotenuse. And again, the beauty of having a hypotenuse of 1 is it makes our numbers relatively nice. And it allows us to do easy division here when we divide by the hypotenuse. So we get root 3 over 2. So that's what's going to go here. Instead of cosine of 30, we're going to write root 3 over 2. So I'm going to copy down the problem. C squared equals 61 minus 60. And that's going to be, instead of cosine of 30, I'm going to write root 3 over 2, because cosine of 30 is root 3 over 2. Now we can do multiplication here. Negative 60 times root 3 divided by 2, we can do it in any order. So I'm going to divide by 2 first. And so I'm going to get 30 root 3. And again, let me break that down. The 60 divided by 2 is 30. Then we times it by root 3 and we get negative 30 root 3 because there was already a minus there. Now we can't subtract these anymore without a calculator. Negative 30 root 3 is going to be an irrational number. So all we can do is get c on its own. Right now we know what c squared is. So we need to root both sides to get regular c on its own. So we get the root of 61 minus 30 root 3. And yeah, it looks weird to have a root within a root, but that's all calculator work. I'd rather circle that, call it a day, have an exact answer versus having an answer that's a decimal that I'm going to have to round. So that is what C is. So the length on this triangle right here is going to be the root of, or whatever the root of 61 minus 30 root 3 is. That's going to be right there. And that's what you get when you have a triangle with a 6 and a 5 and the angle in between them, 30. So what if C, instead of being a side, was that angle? What if we knew all three sides, but we wanted to know the angle? Well, you could use law of cosines to solve that as well. Instead of having this be our C, because we'll know the side, we're going to have this angle, this mystery angle, be our C. So let me show you what I mean by that. So again, here's our generic triangle, because law of cosines works for any and all triangles. And so what if they give you that this angle right here is, let's do 45. And this angle right here is x. We don't know it. They want us to find that angle right there. And maybe the sides of the triangle are given to us. So how about we get 4, maybe 3, and let's have this side be 9. All right, so 3, 4, 9. That's not going to be a right triangle. So bummer there. But we can solve for x using law of cosines. So in this case, c squared in our formula, if you refer back to our law of cosines formula, is referring to a side. So all of our sides we know, so we're going to fill those all in. It is important that c squared, whatever we call c in this diagram, is across from the angle we're looking for, because that's what's going to go here, right? This doesn't give us any other inputs for angles. So we need to make sure the side and the angle that are associated with what we're looking for go here and here, always. So we know that we're looking for angle x. So side C should be 4, and angle C should be x. So Writing the formula, just so you can see it, we've got C equals A plus B, and we've got another AB, and then we've got a capital C over here. Let's see if that all fits out nicely. Trying to do this economically. Squared, squared, plus squared, minus 2, and then the cosine of angle C. Yeah, that worked all right. All right, so we know our sides, and C has to be 4 because X has to be here, and they're associated. So instead of writing C squared, I'll write 4 squared, which is a fun game. A squared is either the 9 or the 3. Let's go with A squared being 9, so A being 9 and A squared being 9 squared. B is going to be 3, so we get 3 squared. And again, we fill these all out. And here is going to be 9 and 3 again. And then the cosine of the angle that we're looking for is x. And again, double check that x is here and 4 is there. Yes, good, we set it up correctly. The common mistake is that people put the 9 or the 3 here, especially the 9 because they think C is always the biggest side, especially when we're doing PFAG. That is not true. C in this case is always the side across from the angle we're looking for. So we don't know what this is, we'll call it x. And now we begin the process of solving. So on this side, we know what 4 squared is. It's 16. Here we get 81 and 9, and then we get minus 2 times 9 times 3. Well, I'm going to do 2 times 3 first, because it's all multiplication. I can do it in any order. 2 times 3 is 6, times 9 is 54. 6 times 9 is 54, and then we get times the cosine of angle x. All right, so we'll combine these. We get 16 equals 81 plus 9, which is a cool 90, minus 54 times the cosine of angle x. And it's tempting to subtract these two, 90 minus 54, but again we cannot because negative 54 is multiplied by cosine of x. What we can do, however, is move this 90 over. Again, our whole goal is to get x on its own, so we need to move the 90 eventually. We need to move separate the negative 54 from the cosine of x, and we need to separate cosine of x from x. So let's move the 90 first. That's just by subtraction. So we subtract from 90 from both sides. Over here, we're going to get negative 74. And that's going to equal negative 54 times the cosine of x. All right, so now we got to remove that negative 54. We're not going to add it over because what's happening between the negative 54 and the cosine is multiplication. And remember to separate things, which is what we're trying to do. We're leaving the cosine of x behind and moving the negative 54 over. We're separating them. Is we need to divide them just like you would do anything when you separate, right? I've got two things here, and if I divide them apart, I have now separated them. So I'm going to separate this by division. And I do that by dividing by the thing I want to move. So I divide by negative 54 to both sides. Negative and negative make a positive, so I've got 74 over 54. We can reduce that later. And that's going to equal the cosine of angle x. So now what I want to do is I want to do cosine inverse to both sides. And when I do that, I get cosine inverse of whatever this fraction is, equals, well, these cancel because cosine inverse and cosine cancel. They are opposites, much the same way that positive 90 and negative 90 are opposites. They are inverses, and we get x all on its own. So we unwrap the cosine by using cosine inverse and got ourselves x. Now, yes, we can reduce this fraction, so let's do that over here. It's going to be cosine inverse of whatever this fraction is equals x. Well, 74 and 54, I was going to say are both divisible by 3, but this one's off just by a little bit. So they're both divisible by 2. So we're going to get 37 here, and here we'll get 27. So 37 over 27, I believe that's as far as we can reduce it. Make sure that my math is correct. 37 times 2 is 74. 27 times 2 is 54. And I believe that, nope, both can be divisible by 3. So I divided by 2 and divided by 3, so this is divisible by 6. That's not right. That can't be. Because 60 is divisible by 6, and we have 66 and 72. So I must have goofed somewhere. So I can't divide by 3 and by 2. Oh, 37 is not divisible by 3. I was thinking 27 for both of these. Silly me. So this is reduced as much as possible. Could you plug this in a calculator and get a decimal? Yes, you could. Knock yourself out. I'd rather not. So x is going to be the cosine inverse of 37 over 27. That's what this angle measure is going to be. So that angle measure is going to be the cosine inverse of 37 over 27. And if you notice, we never really use this 45. And that's because we only have one spot to put our angle measure. And it's always going to be the angle associated with the angle that we're looking for, or the angle associated with the side that we're looking for. So this 45 was useless. Does not matter. So that's law of cosines, their applications. In the next video, I'll be doing the proof for the law of cosines. Where does this beautiful advanced form of Pythagorean theorem that works for any triangle come from? It's actually not that complicated to derive. So we'll talk about that next.